Let's get started. Lecture, wait, is that the right day? But no, it's not. Hold on. That's the right day. That's the right day. Although, for some reason, the announcements are not correct. So let me try this again. Hold on. Everybody get the code? I'm going to copy and paste the announcements from, I don't know why I put the announcements on the previous slide. I must not have been paying attention. Everybody got this? Okay. Wait, hold on. I did put the announcements on this slide. What happened? I don't know. Maybe it didn't sync or something. I don't know, because this is slide 3. This is slide 4. I'm not sure what happened. I don't know. Maybe I'm having a syncing error this morning. I don't know. But the only thing I wanted to mention is that I'm still working on grading your project submittal. The other thing I wanted to mention is this is maybe a bit of good news for everybody in the room. So we have exam 2 next Monday on the 28th. The 30th, I have to be out of town for a day. And I was thinking of like pre-recording a lecture and doing something like that, but I started looking at the very final topic in the class, which is the topic on matrix analysis, and I'm thinking about retooling that a little bit. And so I'm thinking on the 30th, after the exam, I'm genuinely thinking of just canceling class, no makeup homework assignment, no video to watch. We'll just meet back up on Friday. Unless you want me to come up with something for you to do on your that's what I thought. Doesn't take up too much of my time. Okay. All right, everybody get the code? All right, I don't know why this didn't sync or something. I'll look at that here in a bit. Okay, I want to go back to this beam. I'm not going to really do anything with it together, but I just kind of wanted to make a point about something here on the slide that I really didn't have a chance to talk about in class because we ran out of time. And I'm just going to use the deflection to make the point, not the rotation. But here's the problem that we did, and we were determining the deflection here, right? And if you recall, we got a deflection of 0.792 inches downward. Isn't that what we got in class? Is it? Everybody awake? Yes. Everybody moving? This is what we got, right? Okay, so I want to show you something real quick. So the problem, or a problem, I guess I should say, with our analysis is that we did all this math to get the deflection right here, okay? What if I wanted the deflection anywhere? Like, what if I want the deflection here, or here, or here? Let's say I want the deflection at midspan. That means I have to do that all over again, right? The real analysis, the virtual analysis, the integration, all that. So if you want to make your analysis a little bit more general, one thing that you can do is instead of like at 10 feet over, make it, 8 feet over, okay? And so instead of this being 20 feet, it'll be 30 feet minus A, right? Because the whole beam is 30 foot long, right? Now, that won't change your real analysis, but it will change your virtual analysis. And if you're interested in trying this, I'll show you what happens. So your real analysis doesn't change. So you still have 18x minus 0.6x squared, valid from 0 to 30, okay? But if you place this load at A instead of 30 feet minus A, what happens is you get your M delta 1. It ends up being, 1 minus A over 30 times x, and this ends up being, delta 2, ends up being, negative A over 30 times x minus 30. And just so everybody's aware, if you don't trust these equations, like what happens if, note, if A is 10. What if we actually make A the value that we had in the problem? Well, what that means is that M delta 1 is going to be 1 minus 10 over 30 times x. And so what is that going to be? 1 minus a third, or 2/3 x? And that's the same thing we got in the problem, right? And then if we do m delta 2, we get negative 10 over 30 times x minus 30. So that's a third. So we get minus 1 over 3x plus, what is it, 1 over 3 times 30, or 10 minus x over 3. Isn't that the same thing we got when we did this problem by hand? Because we had gotten, this was m delta 1 and m delta 2. So then the only thing you have to do to find the deflection is you say, okay, I'm going to do 1728 over EI, and I'm going to have two integrals. And when we did this by hand, what we had done is we said, let's go from 0 to 10 and 10 to 30. Here we'll do 0 to A and A to 30. Now, this does turn into a little bit of alphabet soup, right? Because you're having to integrate with more, letters in your expression. But if you do this, all you have to do is treat A like a constant and sort of integrate. And you end up getting the following. You get a to the 4th over 20 minus 3a to the 3rd plus 1358. And what you ought to do is see, does this equation work? Well, guess what happens if you take this equation, plug in an a value of 10, and use this value of e and I, you get 792. Okay? So, but the value is now we have an equation that will tell us the deflection anywhere. Okay? Does that make sense? Now, if you really want this to be a robust solution, something to consider is that instead of writing this as 1.2 kips per foot, write it as W. Or instead of 30 feet, write it as L. Okay? Now, will that make a really alphabet soup problem? Yes. But the result is you will get the deflection in a simply supported beam subjected to any load. The beam could be any length, and you can find the deflection anywhere, right? Remember those beam analysis aids that we talked about? That's how they do it, right? So somebody did all that integration for you, and just boom, here's the answer. Okay? Does that make sense? Okay. All right. And again, I'm not making you do all that. I just, although I'll say if you practice that, there's an answer, and it'll probably make the next homework a little easier. So it's just something to think about. All right. Everybody good? All right. I didn't get a chance to talk about this very last slide, but this last slide is really what starts the motivation for our lecture today. This is a note that I wanted to provide on variable cross-sections. So I want to look at this beam. Okay, so this is a simply supported beam with a point load in the middle. Okay, so let's just think this through. So I'm going to have a reaction here and a reaction here. So the shear diagram is going to go like that, and then the moment diagram is going to go like that, right? So I'm going to have moment diagram that looks like this. And if I'm interested in finding the vertical deflection at C, this is my real structure. The virtual structure is a single unit load at C, so it's also going to look like this, right? So both moment diagrams, both the real and the virtual moment diagrams, are going to look something like that, right? So I'm going to need two functions, two real functions and two virtual functions to define the moment diagram. So I'm going to have to do two integrals, right? But the problem is this variable cross-section, that the beam gets sort of thicker in the middle, okay? Which is something that we do in the real world. If you go look at plate girders, for example, in highway bridges, you'll see that the cross-section changes as you get closer to the middle because you have higher moments, okay? So this is something we do in the real world. So the problem is this, okay? So here would be your real functions, here's your virtual functions, but you can't do two integrals, okay? You got to do 4 of them, okay? Because what you've got to do is you have to integrate from 0 to 10, and you have an EI, but then you have to do another integral from 10 to 22 because you have a different EI, right? Then you got to do bam to bam, bam to bam, so you end up having to do 4 integrals, right? That's kind of a pain, right? And so, is there an easier way to do it? Okay, and the answer is yes. Okay, this lecture is, I'm not sure that you would find this lecture packaged this way in textbooks. Like, you'll probably find stuff related to this in various structural analysis textbooks, but this is just sort of putting it all in one place. And so I call this lecture Tips and Tricks for Making Virtual Work Easier. Okay. Going back to this method, we are having to sum up integrals across the span. And the point is that, again, if you respect the principles of static equilibrium, if you respect the basic tenets of calculus, everybody will arrive at the same answer. But there are optimal ways of doing these problems. Okay? So as a result, I want to see if we can cultivate those optimal ways. Like, the idea behind virtual work isn't too difficult. You know, write a set of real functions, write a set of virtual functions, figure out your ranges, and just integrate. Yeah, that's fine, but there can be a lot of algebra, a lot of calculus to go through, and maybe there's ways of making your life easier. Okay, I have 4 tips for you. 4 tips that can make your life easier when computing beam deflections. Okay, and here are my 4 tips. The first tip is to exploit symmetry whenever possible. Okay, if you can exploit symmetry whenever possible, you will make your life a lot easier. And in most real-world structural analysis problems, symmetry exists. Okay, it might not exist on, say, your homework assignment problem, and you'll see why. But if you're just doing like a problem like this, you can probably exploit symmetry in some instances to make your life a lot easier when developing your equations. Okay, that's tip 1. Tips 2 and 3 are kind of related. Tip 2, bless you, is to use a coordinate system at the free end of a beam whenever possible. Okay, and tip 3 is whenever you're cutting a section, always look towards the origin. Okay, and notice how I didn't say look to the left or look to the right. I said look toward the origin. Okay, and the reason I've worded it that way is because of tip 4, exploiting integrals with lower bounds of 0. And the way that we're going to exploit integrals with lower bounds of 0 is maybe to use 2 coordinate systems. Okay, these are the 4 tips. Okay, now each one of these tips I'm going to explain in very significant detail. Okay, so you all can write these down, but I'm gonna go through each one very explicitly, and I'm gonna demonstrate why one. Basically, what I'll do is, like, for example, let's say tip 2. I say use a coordinate system at the free end. I'm gonna show you why this is a good idea by showing you what happens if you use a coordinate system at the fixed end. I'm gonna sort of prove by contradiction, if that makes any sense. And same thing for a lot of these. Okay, sound good? All right, so let's say tip 1. Tip 1 is exploiting symmetry. Okay? The big thing about exploiting symmetry is to just sort of take a step back and recognize what we're doing. What we're doing in these problems is summing up the energy inside the system. Remember, the principle of virtual work is an energy-based deflection method. What we're doing is saying that the energy going in has to equal the energy going out. So our real task is just to integrate across the entire structure. Okay? So these are the functions that I showed you on this past slide, and these are all the integrals that you have to do. That's a pain, right? Okay? To illustrate symmetry and how symmetry can help, let's go back to basic calc 1. So let's consider the following function. F of x equals 6x minus x squared. Notice how this function is not exactly coming out of nowhere. I mean, here's the real moment function on the problem that we just did. Look at the function, 18x minus 0.6x squared. Same kind of idea, okay? Now, if you break out Desmos or Excel or whatever and graph this function, this is what it looks like. It's a parabola. It opens downward. It intersects the x-axis at x equals 0 and x equals 6. Those are the roots, okay? That's your parabola, okay? Now, I give you a challenge. I ask you to compute the area under the curve from x equals 0 to x equals 6, okay? I propose to you that there's 2 ways of doing that, okay? 2 simple ways of doing it. First way is to just integrate from x equals 0 to x equals 6, right? That's one way of doing it. If I wanted to exploit symmetry, though, maybe what I'll do is integrate from 0 to 3 and just double it, right? I mean, won't that work too? Okay? That'll give you the same answer. Go test it out and you'll see, okay? I propose that we can exploit symmetry in the problems that we are doing in this class as long as the structure that we are analyzing is under the following 4 constraints. Okay, first off, it's got to be symmetric with respect to the geometry and the boundary conditions. Okay, so the moment that you have a problem, I don't know, like this, it goes away, right? Because that's not symmetric. Okay, it's got to be symmetric with respect to the geometry and the boundary conditions. It has to be symmetric with respect to the loading. So for example, so far for our first 2 tests, this problem passes, right? Because it is a symmetric structure and the loading is symmetric, right? I can fold the structure on a piece of paper about the middle and I get the same picture on either side. It has to be symmetric with respect to the flexural stiffness, the EI, and it has to be symmetric with respect to the point of interest. Unfortunately, that's where this problem fails the test because the point of interest is sort of over here. If we were interested in mid-span deflection, this problem would be a lot easier, okay? So let me show you what I mean by this on this example that I brought up, okay? So this is the structure that I brought up, and I propose that the old way of doing this is sort of the brute force way, which is integrating from 0 to 10, 10 to 22, 22 to 34, 34 to 44, okay? And I've got to integrate all 4 of those. I propose that the new way of doing it, exploiting symmetry, is to just integrate from 0 to 10, integrate from 10 to 22, and just take that sum and double it. So instead of having to do 1, 2, 3, 4 integrals, I now only have to do 2. And another added advantage is that the functions over here, these functions on this side, are a lot more mathematically forgiving than the others. Because the big M is 4x and the little m is x over 2. So all I'm having to do for both of these integrals is just integrate 2x squared. So suddenly the problem got a lot more handleable because I recognized that I could take into account symmetry. Okay, so instead of having to do 4 integrals, I only have to do 2. That's a tip for making this process a lot easier. Okay, and I guarantee you, this and this will give you the same answer. Okay, does that make sense? All right, any questions on that? Okay, I sort of throw that at you as sort of a real world application to make this stuff easier. Okay, tip number 2, origins at the free end. Okay, this is all about simplifying the algebra and the calculus. Okay, so let's take a look at this problem. Okay, this is the very first deflection problem that we did together. And I think if we did this problem, I think we did it together, and I think the deflection was something like 0.911 inches. I think that's what it was. Deflection was 0.911 inches downward. I think. Don't quote me on that. It might have been a little off. Might have been different. But I gave you a cantilevered beam, and I said I want to find the deflection here, right? Now, one thing that's kind of interesting is that I was a little sneaky in the fact that I drew this. Not only this, but I drew your homework in a very specific way. I put the coordinate system over here on the left. I put the boundary condition over here on the right. So we were cutting sections and looking to the left. And I kept saying we're cutting sections and looking to the left. But really what I wanted you to do is cut a section and look towards the free end. Okay? Let me show you something. Let's take a look at this beam. Do you think that there is anything physically different between this beam and this beam? Let's take a look at these 2 beams. This is a 15-foot long beam. This is a 15-foot long beam. This is 2.5 kips per foot, 2.5 kips per foot. Cantilever, cantilever. What's the real difference between these 2 structures? The fixed end is on the left or on the right end. The fixed end is on the left end. But I guess my question to you is physically, if I went to the lab and put 2.5 kips per foot over a distance of 15 feet on this beam, would I get the same deflection at the free end? It would behave the same way, right? I mean, the physics isn't going to change. Okay? So I've defined the origin at the free end. And this is what we did in class. Okay? So let's summarize what we did in class. Okay? So we define the origin at the free end. Remember, we cut a section and looked this way, right? And what we got was a real moment function of negative 1.25x squared, a virtual moment function of negative x. So we multiplied those two. We got a little m big M of 1.25x to the third, right? Integrate that from 0 to 15. You can do that in a Casio FX115 ES Plus or similar scientific calculator, and when you chuck that out, you get 15,000, And there is actually a very specific reason I'm going out to so many decimal places. You'll see this here in a second. Then what do? We take this, multiply it by 1728, divided by EI, and we got, oh, I got it right. It was 0.911 inches downward. That's what we got, right? So far so good? Now, I propose this is a lot easier than if the boundary condition was over here, okay? Why? Because if we cut a section and look to the left, we have to account for the reactions, right? So here, if I cut a section, look to the left, I've just got the distributed load to deal with, right? If I cut a section, look over here, I've got the distributed load, I've got this and that. So the problem is the real moment function and the virtual moment function are a lot nastier, right? I got to deal with all this foiling and all that. And so if I take this, take that, so I got to do x, 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 I got to do 15, that, you know, collect like terms, and I get this monstrosity. Then I have to integrate it from 0 to 15. What happens if I integrate it from 0 to 15? I get the same answer. Because the beam doesn't care. The energy in the beam is the energy in the beam. These two expressions are expressing that energy just from a different origin. So if you define the origin at the free end, you will make your life a lot easier. Okay, that's my point on this exercise. So far, so good. That's tip number 2. Okay. How are we doing? So far, so good. Okay. Tip 3. Always look, when you cut a section, look towards the origin, okay? This is all about simplifying just the algebra, okay? Now, I said a while back, I said, listen, if I'm sitting here on this table, and you break out the samurai sword or lightsaber and cut through the table, I'm falling to the ground, right? And the reason why is because we are releasing from the structure the ability to resist forces in the x direction, forces in the y direction moments right here. But it doesn't matter whether I look to the left or look to the right. I am going to get the same answer. That doesn't mean that there aren't optimal ways of making the algebra a little easier. Okay? So, let's cut a section. Okay? So you agree with me, by the way, that hopefully tip 2, you agree with me that defining the origin at the free end makes sense, right? Cutting a section here, looking, that makes sense. So this light sensor, I stand in front of it, the screen gets darker. All right. Now let's cut the section, okay? Again, either side will give the same answer, but one way is easier. Let's take a look at something. Okay, so I'm breaking out the samurai sword or lightsaber, and I'm cutting a section, okay? Now if I cut a section and look to the left, what is this distance right here?
X.
X. So if this is X, what is this distance?
L minus X.
L minus X, or in this case 15 minus X. 100% right. Keep that in mind. Okay. So if I cut a section and consider the free body diagram to the left, would everybody agree this is what it looks like? So I've got the distributed load, I've got the X, I've got V, M, right? So what do? We break out the sum moments, right? We break out our little table, put all the moments going this way, all the moments going that way, right? So what do? We say, okay, I've got M of X going like this. I've got 2.5x times x over 2 also going like that, right? So I'll say, okay, M plus 1.25x squared equals 0. Done. Right? That's easy, right? So what happens if I cut a section and look away from the origin? So if I've defined my coordinate system here and I cut and I look this way, I've got this to deal with. Okay. Let's see. Let's sum moments. So what do we got? We got the M going like that, right? We've got the 2.5. Oh, wait a minute. It's not 2.5 times x over 2. It's 2.5 times this distance. This is not x. This is 15 minus x, right? So it's 2.5 times this distance over 2. Ooh, we got to break out the foiling. We got to do that, right? Okay. Then, ooh, where'd that 281.25 come from? That's this, right? Then we have this reaction going the other way. Okay. Algebra time, everybody. All right, so we're going to collect all this together. So m plus this, so this is 1.25 times that, plus this equals that. Okay, so what are we going to do? How do we get from here to here? Well, let's take this and FOIL it, right? Let's take the 37.5 here, 37.5 here, right? Now we got a 1.25. Take the 1.25, distribute that out. So 1.25 times this, 1.25 times this. Da, 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 da. Let's collect the like terms, because I got a number here and a number here. Combine the numbers. I see I got a 562.5, 62.5, cancel. Negative 37.5x, negative 37.5x, cancel. And I'm left with this, or the same thing before. Same answer as before, right? But this is a heck of a lot harder, isn't it? Right? A heck of a lot harder. See what I mean? Y'all are going to be doing stuff like this on the homework, and what I'm trying to do is prevent you from going up to one of the third floor classrooms and filling up the whiteboard, you know, all the way out when you could take the calculations and make them like this. Does that make sense? So, when you cut a section, it is generally advantageous to look towards the origin. It is generally advantageous to do that. Okay? Make sense? Any questions on this? All right. My next tip is a little more esoteric. Okay? Zero lower bound integrals. Okay? So let me explain what I mean. Let's take a look at this beam. Okay? I've got an overhanging beam, and the load doesn't really matter. It's some variable, right? And there is no way of getting around doing at least two integrals. There's no way of avoiding that, because, like, if you cut the section, right? Remember, if you cut a section, you say, okay, I move the section cut over, and then as soon as I get there, I have another load to consider. There is no way getting around doing at least two integrals for this problem. But we can orient the coordinate system to our choosing. Like, we can put the coordinate system however we want. We can also place the origin wherever we want. Okay? And ultimately what we need to do is sum the energy in the entire system. So I propose using two coordinate systems. Okay? I propose actually putting one origin here and another origin here. So one coordinate system goes this way and one coordinate system goes that way. And some of you might be thinking, well, doesn't that make the problem harder? I propose no. I propose that it will actually make the math and the algebra a lot easier. Okay? Let me explain. It goes to the tip, and the name of the tip is at exploiting integrals with a lower bound of 0. To explain that, let's go back to Calc 1. How do we evaluate a definite integral? Right? If we have the definite integral of a function, we figure out its antiderivative, and then we plug in the top number, minus plug in the bottom number, right? Fundamental theorem of calculus, right? We, in this class, and in the main type of analysis that we're dealing with polynomials, okay? And when you integrate a polynomial, the plug and chug part is a lot easier when the lower bound is 0. So just to make the point, let's integrate this. Let's integrate f of x equals 8x to the third minus 6x squared plus 5. So if I throw an integral on that and integrate it from 0 to 4, okay, so what do I got? The integral of this is x to the 4th over 4, so that's 2x to the 4th, right? This is x to the 3rd over 3, so 2x to the 3rd and 5x. So I'm integrating this from x equals 0 to x equals 4, right? So what do? I plug in the top number minus plug in the bottom number. What happens to all this? 0, right? So I can make the integral a lot easier if one of those lower limits, or one of those limits is 0, the math becomes so much easier, right? So here's my point. Let's go back to this problem, okay? So if I use one coordinate system, if I just put an origin right here and say this is my y-axis, this is my x-axis, I'm going to integrate from 0 to 30 and from 30 to 46, okay? That's if I use one coordinate system. If I use two coordinate systems, again, all I've got to do is sum the energy up across the entire structure. So I propose I can use this origin and integrate from 0 to 30, and then use this origin and integrate from 0 to 16 this way, okay? So I've got two integrals with a lower bound of 0. Makes the plug and chug a lot easier, okay? And it will typically make the functions themselves easier, okay? Make sense? Now the only thing about flipping the coordinate system is that if you're using the point slope formula, like remember how we were drawing virtual functions and we were just using the coordinates? You gotta flip the slope, the sign of the slope, because what happens is, here's the line. If I change the orientation of the coordinate system, right? If this is the coordinate system, and then I reorient, the line goes the other way. That's not really a big deal. It's just something to keep in mind that if you're using the point slope formula to find the slopes, you just gotta flip the sign on your shear diagram. That's all. And don't worry, I've done a lot of stuff with you today, and I think it is best conveyed by just having a nice little interactive example. Okay. Now we're not gonna like chug this example out. We're not gonna do it. I've done the example here on the slide. This is mostly to absorb what I'm talking about. Okay. So if anything, what I'm doing is I'm giving you an example, and I'm giving you the answer to this example, so that if you want to try it out on your own, you're more than welcome to. Okay. Okay. So here's the problem. We're going to determine the deflection, or sorry, the displacement at B. Oh, whoops, that's a typo. Oop. Displacement at C. This is a brand new example. This is the first time I've done this, so whoopsie. We're going to determine the displacement at C and the rotation at E on the beam shown. Okay? So let me put this here on the board, so I got a little something to here to reference. All right, so we'll put and so this is 3 kips per foot. This is 2 kips per foot. Okay. All right. And I'm purposefully not putting much else on the board beyond that because I'm going to show you something here in a bit. But we're going to find the displacement at C and the rotation at E. And I've given you the E and the I value. Okay. So let me go through a couple of questions with the class. How many moment functions am I going to need to define the real moment diagram? How many? 3, right? 1 from A to B, 1 from B to D, 1 from D to E, right? Everybody with me on that? Okay. So here's the structure. We agree we need 3 moment functions. Okay? We're going to take advantage of the 2 different coordinate systems because remember we said one tip is to put coordinate systems at the free end, okay? And we have a free end over here, and we have a free end over here. So the way I put that here on the problem is I just sort of said, okay, let's just have one like that, and let's just sort of have one like that. So we'll call this x1 and y1. We'll call this x2, y2, okay? All right. So what we'll have, this is what we're going to have. We're going to have some real moment function that is a function of x1 and is valid from 0 to 10. We're going to have another moment function in terms of x1 that's valid from 10 to 40, and then we're going to have a third, which is in terms of x2, valid from 0 to 10, okay? All right, so the first moment function is going to be from here to here. The second is going to be from B to D, and it's going to use this origin, and then the third one is there. Now, I'll say something about the second one. Some of you might ask, well, couldn't this function in the middle, couldn't it be written in terms of this coordinate system? And the answer is, yeah, it could. It actually could. Is there a preference one way or the other? Not really. The big point is that it would be a lot easier for this segment to express it in terms of that coordinate system. The main reason for the second coordinate system is that segment right there. Is everybody okay with that? Okay. All right, so these slides are basically the answer. Okay, I'm actually putting all the math here in the slides because I don't want to spend the next 30 minutes just writing a bunch of alphabet soup on the board. I want you to get the idea. And also, I am summarizing the answer because you ought to try this on your own and see if you come up with the same answer I do. Okay? With me so far? Okay. Okay, so let's look at the real structure. So notice I went ahead and put the support reactions there. I'm hoping that you all could do that. Okay? So this reaction here is 68.33 kips. This one right here is 61.67 kips. Now I'll go ahead and tell you on the slides, I did actually go ahead and put them in fraction form as well, but my reason for doing that is not because of a need to adhere to a mathematically pure expression of that value. It's mainly because if I write these things in fractions, the formulas are small enough that I can fit them on the slides. So I didn't want to crowd the slides, so I'm using those fractions, quite frankly, to just suck the formulas in a little bit. Okay, so I decided to break out my favorite computer program, which is Excel. Okay, so this is what the moment diagram looks like. Okay, so if you plot the moment diagram, I get a linear moment diagram here, a quadratic moment diagram here, and a quadratic moment diagram here. Okay, I'm hoping that everybody kind of believes that at this point. I mean, I have a distributed load here, so a linear shear quadratic moment, same thing here. No load here, constant shear linear moment. So I'm hoping that works. And I went ahead and derived the equations for you. Here's the equations. Boom. There they are. Okay? Now, I think that M1 and M3 are pretty easy to see. And honestly, pretty easy to see just by observation. I mean, if I cut a section right here, right? If I cut a section right here, I have 20 times x, right? 20 times x. You know what I mean? Cut a section over here. 2x times x over 2. X squared. They're negative because of the fact that both the unknown and the moment go the same way. But I'm hoping that that is simple. Okay? Now, I will tell you that this equation here takes a little bit of algebra to get to what I got on the slide. And I'm going to show you what I mean by that. Okay? So let's do this one together just to sort of make the point. Again, I'm not putting this in the notebook because I want you all to follow this on your own. So let's cut a section. Okay. So this dimension here that's x1, right? What is this dimension here? What's that dimension?
10 foot.
10 foot. So what's this dimension?
10 plus. Oh, wait. X.
Say it again.
10 minus X.
Is it 10 minus x or is it x minus 10?
X1 minus X minus 10.
X minus 10. Because if this is like 16 feet and that's 10, that makes this 6. Because it's x1 minus 10. Make sense? Okay. And so what we'll do is we'll say, okay, this is 3 kips per foot. if I collapse that into a single load, how much is that load? How much is that load?
3x minus 30.
Say it again. What'd you say?
Is it 3x minus 30?
Yeah, because what you're doing is you're saying 3 times that. That's what you're doing, right? Okay. And then this distance right here is what?
x1 minus 10 over 2.
Right? So it got a little more complicated. It did. I don't think we could have avoided this complication. I think we just have to embrace it. But I think we've used about every trick that we can. So this is shear. That's moment. So let's see what we can see. So we're going to have 20 times x1. We're going to have 68.33 x minus 10, and then we're going to have 3 over 2 x1 minus 10 squared, right? You see how I did that?
Yeah.
Because it's 3 over 2 times that quantity squared. So we're going to have 68.33. I'm going to avoid the subscripts because I'm going to get tired of writing them. Right? Everybody see that? I am also, instead of 68.33, instead of that, I'm going to write 205 over 3. Okay, so let's see what I can come up with. So over here on this side, 205 over 3x minus 2050 over 3. See what I'm doing? Okay. Equals 20x plus 3 halves. All right, so what do we got? X squared minus 20x plus 100. See what I did there? Boiling, right? So 205 minus, okay, so this is going to be 3 halves times negative 20, so 30, right? Did I do that right? Because the 2's cancel to 10, and then this, 150, 450. Did I do that right? Wait, is it 450?
Isn't it
150. 150. I'm doing this freestyle, so bear with me. Okay. So
Is
what's
this supposed to be an M or not?
Oh, yeah, you're right. That's an M. Yeah, plus M, plus M, plus M. Thank you. You're 100% right. You're 100% right. So yeah. So now let's get everything over to the other side. So we'll have an M over here, and what do we have over here? So let's deal with the x squared term first. So negative 3 halves x squared. Okay, what about the x terms? So what do I have? 205 over 3 minus 20 plus 30. And then what about the constants? So I've got a negative 20, 50 over 3 minus 150 equals m. And I think if I did my algebra correctly, that ends up being 235 over 3, and that ends up being negative 2,500 over 3. I can eyeball that and see that one's going to be okay. So, you see, that's what I'm saying. Like, this one took a little bit of work to get to. So, everybody good? All right, any questions on that? We're doing good on time. Okay. So for the virtual moment functions, now the virtual moment functions are kind of easy, right? Because I've got a virtual force right in the middle, right? Okay. I've got, so if this is 1, that makes each of these a half, right? So the shear diagram goes up like that. The moment diagram just looks like this. So here the moment is 0. Here the moment is 0, and here it's linear, right? So really all I care about is just this line and this line, right? So we'll call that M delta 1, delta 2. This is from 10 to 25, 25 to 40, both in terms of x1. They've got it both in terms of x1 because this is in terms of x1, okay? Sound good? So once I do that, I find that it's a lot easier to set this up in a table. Okay, so let me show you what I've done here. So I've got a table here. Let's look at our range. So I'm going to look at AB, BC, CD, and DE. Okay. For A through D, it's in terms of x1, and DE is in terms of x2, right? Okay. Now look at my real moment functions. Okay. Why do I have this written twice? Because this is valid from 10 to 40, right? So this entry shows up twice, right? Okay? I have to have 2 entries because I get different terms here, right? See that? Okay, and so now I'm going to integrate. What am I going to integrate? Okay, I'm going to integrate that times that from 0 to 10. That times that from 10 to 25. That times that from 25 to 40. That times that from 0 to 10. Okay, for the top and the bottom, there's 0, right? There's nothing there, right? And then the only ones that actually give you values are from the 2 middle ones. And again, I'm leaving them in fractions because if you calculate it out, it goes out. So, all right, sum that up, that's what you get. 1728 over EI times the sum, I get 0.419. 0.419 inches to going down. That's the answer, okay? What about the rotation? Okay, what do? Take all the loads off, put a rotational moment here at E, assume a direction. I get 1 over 30 going up, 1 over 30 going down, equal and opposite. It's a force couple. So that's what our moment diagram looks like. I get a 0 moment here, linear, and then a constant moment here of 1 because that jumps it right back down to 0. So what do my functions look like? For x1, x minus 10 over 30, or sorry, for x2, it's just 1, just a constant moment of 1. So set up the same table. I don't have the BC and the CD because it's all the same. There's my ranges, there's my real moment function, there's my virtual moment function. So the funny thing is, I never actually used this function in the entire problem. I never used this one at all. So integrate sum. This is the only integral, by the way. This one, an integral actually does come out negative. That can happen. So if they all come out negative, it means your assumption was incorrect. But it is possible. It is also possible that you get a deflection of 0, and so you get positive and negative integrals cancel each other out. That's possible too. Sum it up. 144 times 180 over pi, 1 over EI, plug and chug. You get 0.141 degrees rotation. Does that make sense? Okay. I wanted to throw out sort of what I would call a nasty problem. I mean, this isn't as nice as this one. This one is a lot nicer than that one. Okay. But you've got a couple problems on the homework that are little not rough, but I mean there's going to be some algebra there, and so I wanted you to see one that's kind of on the same caliber, so that when you start doing the homework, it doesn't hit you like a bucket of water. Okay. You're like, we don't want to talk about fluids. Bucket of water. Gravity. What's so specific about it? All right, now, that's a joke. All right, everybody good? Should I throw a Reynolds number on here just to have fun with it? All right, that's all I got, everybody. I'll pull up the code one more time, and I'll see you all on Wednesday.